welcome back to another full week, which means we have two different objectives that we're going to talk about this week. The first is going to be to determine the complement of a given set. So if you want to make sure that you've got materials ready for notes, and you can either print, again, the notes, the blank notes that are attached to the assignment, or you can just get out a notebook and be ready to go. So let's get started. Now the first thing we want to do is define what a complement is. So you might think about it as like a complementary angle, and it's really similar. It's the elements that are not in a set. And this would be denoted, so if the given set is A, the complement of A would have this little bar over the top. And what's really important to notice about this is that the elements not in A depend on what we call a universal set. So the complement of A is the universal set minus any element in A. Now, this universal set is really going to be specific to the types of problems. Common universal sets are maybe the natural numbers, the integers, etc. And you can imagine that the complement changes depending on what the universal set is. So if it's taken out of the natural numbers, that's going to be different than if the universal set is the integers, for example. Now, let's look at one such complement. So let's say that P is equal to 2, 3, 5, 7, etc. is defined as the set of prime numbers. Find the complement of P in the natural numbers. So as you can see, the definition of the complement is the universal set, which in this case is the natural numbers, minus the set we're given. So if we take the natural numbers here and we subtract away the prime numbers, so take away the ones that are in common through here, if we listed out the elements, the complement of P would be 1, then 4, 6, 8, 9, 10, not 11 because that's prime, 12, and so on. So you could list them out like this. Another easier way to list them out is you'll notice that with prime, there's already a pretty natural complement in the natural numbers, and that is the compound numbers, which are the ones, not compound or composite. And so you can also just call this the complement of P is 1 union X, where X is a composite number. So this is another way you could write this set. All right, let's look at a less familiar example with graphing. So given the sets, we've got A, which are the ordered pairs x, y on the coordinate plane, r squared, where x squared plus y squared is greater than or equal to 9. And another set, or that should say B, is equal to the ordered point x squared, where x is in the real numbers. So if we're looking at the universal set r squared, that would be this entire coordinate plane. Now, what I'm going to do over here, just like before, is I'm going to graph A and B separately. Now, the first, if we think about x squared plus y squared equals 9, that is the equation for a circle with radius 3, centered at the origin. And then if we're interested in those values that are greater than 9, that would be this shaded region all the way around. And you don't have to make your drawings extra, neat or anything like that. Like, this is fine, just showing the shaded region. Then x squared, if you think about this, is the same as x and y. So y is equal to x squared, and that would be our parabola. So A is this big shaded region, and B is just the simple parabola there. Now, if we're shading the complement of A, the complement of A would be everything that is not in this shaded region, i.e. it is what is inside the circle, and we take away the boundary. So remember, when we don't include the boundary of an inequality, we make it a dotted line, and then color in that whole center area. And this would be the complement of A, where the universal set is the coordinate plane. Now, if we're looking at the next one, B, this would be A complement intersect B. So it's everything that's in this colored in space that is also in B. So if we're looking at this image, we are talking about this part of the parabola here, hole at the boundary. Let's make that a nice open bound. Same on the other side. And that would be A, complement of A intersect B. Would be just that dark spot portion of the graph right there. All right, next we're going to look at proofs and disproofs. So in this first one, it says prove or disprove that the complement of A union B is the same as the union of the two complements. Now I'm going to start off just now because I want to teach this lesson specifically. This is actually not true. You can't sort of distribute the complement like this. And in order to prove something isn't true, you don't need to make a whole big proof. All you have to do is show one counterexample. So if you've got a whole complicated formula, but you can show it doesn't work for 7, that's enough to show that it's disproven. All you need is one counterexample. So in this case, this isn't true. You can't, as I said, you can't sort of distribute the complement like that. And I'm going to prove it with a pretty straightforward counterexample. I'm going to say that A is equal to the set 1, 2, B to 2, 3 with a universal set of 1, 2, 3. Now, as I said, we can show that this is disprovable really quickly by just saying, all right, well, let's compare this first set, which would be the complement of the union, which the union is 1, 2, and 3. So the complement of that, given the universal set, is empty, versus the complement of A, which would be 3, union the complement of B, which would be 1, gives us the set 1, 3, and since these two are not the same set, that means that we have disproven this proposition. All right, let's look at one where we are doing a proof. So instead of saying that we are distributing the complement, we're going to say, okay, well, this one, I will tell you right now, is going to be a proof that A union B's complement is equal to the complement of A intersect the complement of B. And if you aren't sure if it's a prove or disprove problem, just try a counterexample and see if it works. For example, if I looked at the counterexample I made here, and I just changed this to the intersection, then it would work out because then it would also equal the null set. So if you're not sure, just try a simple counterexample and see how far you get. So since this one did work with our first counterexample we tried, we are going to set up our proof the exact same way that we've talked about before in last week plus last week's quiz. We're going to start by saying that we have an element in this first set. And we want to show then that X is an element of this set. So if we know that this is true, that's the same as saying that X is not an element of A union B. Right, that's the definition of complement. If something is not an element of a union, that means X is not an element of A and X is not an element of B. Because if either of these were true, then it would be in the union. So therefore, if X isn't in A and X is not in B, we can also say that then X is in the complement of both of those. Because if it's not in A, then it's in its complement. And if X is not in B, then it's in the complement of B. Now, since we're using the word and here, that's the same as the intersection. So therefore, X is in the intersection of the complement of A and the complement of B, which, as you can see, is what we want because that's the other side of our proof. So now what we've done, so you can say, therefore, using the 3 dots, therefore we know that the first set, A union B in a complement, is a subset. Every element in it is also in here. So now we know that this is true. Now we just have to show that the opposite is true. Now that we've completed one side of the proof, the other one's going to follow really similarly, and this is generally going to be the case. So we're going to say, oh, well, x is in the intersect of the two complements, so therefore x has to be in those two complements separately. Since they're in the complements, that means that x cannot be an element of either set, not in B. And so then if x isn't in A and x isn't in B, then x isn't in the union of those two, and therefore x must be in the complement of that union. So now we've shown that therefore the union, the intersect of the complements is a subset of that first set. Now our conclusion, since these two are subsets of each other, therefore our final conclusion is that they must be equal. And at the end of our proof we can write QED or just the little black box. Let me know if you have any questions about complements in the comments here below, or you can shoot me an email or sign up for a tutoring appointment. I'll talk to you later. Bye.